So, hi everyone. I am Gabriella Di Genova. I'm a second year PhD student at the University of Perugia, and I'm a theoretical chemist trying to become an astrochemist. So today we'll talk about sulfur reactivity on ice in the context of the interstellar medium. So let's start from the beginning. A long time ago, in a galaxy not so far away, there was a cold cloud of gas and dust in an interstellar medium broken in clumps and filaments. Then, 4.5 billion years ago, the small cloud became the solar system. When, why, and how did it happen? Did the Earth receive an heritage from those old eons? Can this heritage help us understand our origins? So, these are some of the big questions in astrochemistry and in astrophysics, of course. And I just wanted to stress the fact that this is part of a super big puzzle. And of course, the goal of today's presentation is not to solve this puzzle, but just to tell you how big, let's say, this problem is. Just to give you a bit of context and to try to make you understand what are we dealing with, I show you this beautiful picture done by one of my colleagues, Marta De Simone. And this is the interstellar medium cycle. So we start from a diffuse cloud, which then can start to become a bit more dense, and eventually they start to collapse due to the gravitational force. And then we have the formation of the first protostars, and eventually the protoplanetary systems, the stellar system, like our own, the solar system. And then eventually the star will start to die, and the cycle will begin again. Now, something that is in common between all these phases is that they all share, let's say, what is the matter that is in between them, which is the interstellar medium. It's of course composed by 99% of gas and only 1% of dust. Now, even if it's only 1%, it's still quite important because it plays a very relevant role into the molecular complexity of the interstellar medium. Now, one small piece of this huge puzzle is the sulfur depletion problem. So this is something that has been challenging the astrochemistry community for a while. Why do we care about sulfur? So sulfur is one of the main 6 components of life as we know it. So it's part of proteins, of sugars, vitamins, so it's quite important. It's also the 10th most abundant element in the universe. It has an abundance of 1.3 10 to the minus 5 relative to hydrogen. And it has been detected basically everywhere, so in interstellar and intergalactic contexts, on planets, moon, comets, it's everywhere. And in diffuse clouds, so the first stage of the cycle that I showed you earlier, the abundance is fine. So the amount of sulfur that we expect to be there is there. This is different instead in the case of dense clouds. So something happens in there. We don't know where is this missing sulfur, so there is quite a lot of depletion of this atom. There are, of course, some theories, so we expect it to find, for example, in solid state forms or in species that are not able to detect with our instruments. Now, I also mentioned the ice in the title of my presentation. Why? Because ice can act as let's say a catalyst for the reactions that happen up there. And it's also, of course, ubiquitous in space because, as you can imagine, it's a bit cold up there. So you can find it in interstellar icy grains, which are this thing here. So there is a nucleus surrounded by an icy mantle composed by dirty ice. So we can find, of course, mainly water, but then other species. And for example, we can find sulfur precursor species. Now they can, of course, interact with the radiation, such as UV photons or the Lyman alpha radiation, and then yield atomic sulfur. Ice is, of course, also present on icy planets and on comets. This is a beautiful picture of the comet 67P Chury that some of you may know about. Now, I will focus on sulfur in its excited state. Why do we care about the excited state? Is the first one, so the singlet D state. The gap between the fundamental and excited state is around 130 kJ per mole. It is a metastable state. It has quite a long radiative lifetime of 36 seconds. It has been proven to give very fast reactions. And it reacts in a peculiar way because it's able to both insert into sigma bonds, but also to addition to lone pairs or pi systems. Now, the idea of dealing with excited state species is not new. So the group of Karin Oberg and Eric Herbst, which are big institutions in the astrochemistry community, have already worked with oxygen in excited state. So it behaves in a similar way of sulfur. It also has a very long radiative lifetime. In this case, is around 100 seconds. Now, let's focus on the case of the comet 67P. On this comet, a lot of sulfur-bearing species have been identified after the Rosetta mission. You can find very simple molecules, but also more complex ones. So we have, for example, a molecule that's composed by 4 carbon atoms. It is quite complex indeed. Or a molecule that contains both oxygen and sulfur atom. This is also relatively complex for us. And the issue is that we don't know how these molecules are formed. There is, for example, no reaction reported for the formation of these species here. So our goal is to try to understand how some of these species can be formed, for example. Now, these are the main precursors of sulfur singlet D that have been identified. And again, if they photodissociate via UV-induced photodissociation, for example, they can form singlet D. And then, of course, before checking out what would happen when the sulfur reacts with other species, we need to check out what happens when it reacts with water, because it's the most abundant component on ice. So we started from the gas-phase reaction of water and sulfur. And here I highlighted the way in which it reacts. So it both addition to the lone pair or insert into the OH bond directly. Something that I would also like you to notice is that there is only one exothermic channel. Now, why do we care about that? Because endothermic channels will not be feasible in the interstellar context. There is simply no way that they would happen. So the only feasible channel is the one that leads to the formation of OS and molecular hydrogen. So we wanted to see what would happen when we include the effect of the ice matrix. So how does the reactivity change? We started a collaboration with Professor Albert Rimola and Jessica Ferrero at the University Autónoma of Barcelona. They are quite expert of ice simulation, so they work with both small and very big clusters of water. I isolated the single processes just to make it more clear. So you can see that the conversion process from this molecule to this other one, min2, is connected by the transition state 1. Now, how does this transition state looks like? So you can see how the hydrogen transfer between the oxygen and the sulfur is quite of a constrained process, right? So the hydrogen has to move from the oxygen to the sulfur inside the same molecule. What happens when we move to the ice matrix surface? So you can see how the barrier is lowered by around 30 kJ per mole, which is a bit. And let's now see how the transition state looks like. So here it's very visible how the hydrogen transfer process is actually mediated by an increased number of water molecules and not just by one single water molecule. So of course this process is easier, and that's a clear effect of the catalytic role that the ice plays. This is even more visible for the second process, so the conversion from min2 to min3. Here the barrier is lowered by more than 100 kJ per mole, so it's quite a lot. Now, just to do a brief recap, we have seen how sulfur singlet D is able to both insert into OH bonds and to add to lone pairs of the water molecule. We have seen how in gas phase we can form sulfur monoxide and molecular hydrogen. We have also seen how on ice matrices we can form species containing sulfur and oxygen atoms, such as HSOH and H2SO. We have seen how ice can play a catalytic role, of course. It's also able to dissipate some of the excess energy, but it also acts as a real reactant with sulfur. And brief spoiler, we have also started working on a possible formation reaction for this molecule here, and we may have found a path. So it's simply the reaction of sulfur with methanol, but it's doable. Let me thank all of the people that have worked with me on this project and the project funding my PhD, and of course all of you for your kind attention. Thank you.
We have time for one quick question. Yes, at the back.
Nice talk, but I couldn't find the ice, meaning what is the qualification that makes your 18H2O molecule ice?
What do you mean? Like how we can say that this is a nice structure?
How, so you freeze some of the modes of the H2O molecule. So what makes to think you that okay, I made a cluster of 18H2O molecule and it is behaving like ice? Why it is so?
Well, I mean, I would say that. Well, here maybe is enough. So first of all, this is an amorphous structure. I forgot to say that. I mean, it's visible. But that's enough for us. I mean, of course, all these molecules are kept together by hydrogen bonds, right? And they're not moving away from each other. So I would say that this is enough to represent a matrix, which is not a gas phase one.
No, I'm thinking of making a solid state structure of these H2O molecules and do a periodic boundary. Is it possible?
Yes, of course. I mean, the group of Albert Rimola has also done that. But for this simple reaction, this was enough for us. And we were able to push the level of theory by quite a lot. We ran, at the end, the LPNO calculation, so that was nice to have.
Thank you.
One more question over there.
So, thanks for the talk. This is a general question about these barriers. How does that relate to the astro temperatures, the low temperatures? So some of them, in one of the slides you showed a barrier that's about 1 electron volt, right? So that isn't that the 120 kilojoules per mole. If I convert it, it's about.
So 10, you're talking about this process here.
Yeah. So isn't that like an infinite temperature versus any astrophysical process?
Maybe this is a bit confusing, so I'm sorry about that. But these are isolated processes, so this is not an endothermic reaction, right? So of course, I mean here I indicated it as a 0 point. But you have to also take into account the amount of energy that derives from the interaction of the sulfur atom with the cluster, which is a lot, is about 280 kilojoule per mole. So you have to imagine a super high energy content, which is available then to for this system to evolve. So we would have enough energy for this barrier to be overcome.
Okay, thanks.
Was I clear?
I think so, yeah.
Okay.
I think we can have further discussions during coffee. Oh, maybe the last one. Yes, that's true, we have time.
I will fast. Really, thank you for really nice talk. I'm curious, are you opening any new channel with this ice? So something that was endothermic before and now is becoming exothermic really?
Well, what it was interesting for us, let me go back to the gas phase. So here, oh, sorry. I'm getting there. Maybe. Okay, here. So what was interesting for us was to check if these species, such as min2, min3, or min1, can be stabilized. So not only the products here, which are actually even simpler than these molecules, but these more complex species. The issue is that in gas phase, we wouldn't have any way to dissipate all this energy content, so these wells are quite deep. But when we move to the ice surface, of course the ice acts as a as a third body that is able to redistribute all the energy, so we can stabilize these molecules. And actually we have started running kinetic calculation to compute the lifetime of these species. And we have seen that actually this species here is very stable in the sense that it has a very long lifetime, and once formed can stay there. And yes, this would be a pathway to form it.
Interesting. Thank you.
Thank you.
All right, let's thank Gabriella and all the speakers of this session.